Hello, class. I looked through your demo book submissions along with the comeback can LOL charts, and I thought I might break down what I think they would look like and see if we have similar ideas and maybe help you polish up how an LOL chart works. And then I want to show you a new demo. But first, let's have a smile. So I want to show you something that, makes me smile every time I see it. Every single time. Oh, that looks so uncomfortable. I do want you to know, she just got a couple bruises. You'd think it'd break her face, but she was actually okay. Her face won that battle, and it is a battle of energy. Okay, let's take a look at the comeback can. You can look back at the video and the other link if you want, but remember, Jacob rolled the can away. The can came back to him. We discussed before that as the can rolls forward, the weights hang down, and because the weights are hanging down, the rubber band can't move in the center. So on either side of the weight, it spins up, storing energy. Eventually, it takes all the kinetic energy and puts it as potential energy in the rubber bands. All right? The can will stop moving forward at that point. And because the rubber bands are tight and they want to unwind, they will begin to unwind and roll the can back. Okay? And it turns that potential energy back into kinetic. So the LOL chart, what I thought it would look like is something like this. When he gives it a shove, in the comeback can, when he gives it a shove, we have kinetic energy. All right, that total mechanical energy is basically kinetic energy. I thought maybe you could throw in a little bit of other energy there, like technically as soon as that can starts to move, the rubber band starts to roll up and wind up. So there's a little bit of potential, and every time you stretch a rubber band a little bit, there's a tiny bit of heat that happens because you stretch a rubber band a lot, it gets hot. So there might be those breakdowns, but for the most part, the total energy is kinetic energy. Now, once the can rolls away and then stops moving, that's over here. What happened is that total energy is now mainly potential energy. But again, because you've wound up a rubber band, you've stretched a rubber band, the rubber band actually gets hot. So there's a little thermal energy. That was my idea. That was my thought on it. And I hope it makes sense. If it doesn't, leave a comment to me someplace. Send me an email, ask a question. The next time we meet, do a Google Meet, which is actually Friday. And thank you for those of you that checked in. It was good to see your faces. When we do it on Friday, you can ask more questions about this because I'm going to start giving you, assessments based on your ability to kind of break these things down. It's not important that what you have lines up perfectly with what I have, but you have to have an understanding of the total energy has to equal the sum of these things, all right? And the energy can change form as something happens in the demonstration, in the comeback can. So, for practice, and for your next assignment, you're going to do an LOL chart for this demonstration. All right, the demonstration we're going to take care of right now. And the name of the demonstration is Tea Bag Rockets. So rockets made out of, a cheap tea bag. Okay, I've dumped all the tea out. You're going to see what it looks like. Go ahead and write down the title and get ready to write down some observations. You can make a prediction, but why don't you watch the video first? So take a look at this.
For this demonstration, and this is a demonstration you can do at home as long as you have an adult nearby and decently high ceilings, just in case. It's called the Tea Bag Rocket, okay? So what we have are 4 empty tea bags. I just had the cheapest possible tea bags I could find. I took all the tea out and I made them like cylinders. So if you take a look, they're just cylinders of light paper standing up. What I'm going to do is I am going to touch the top of each one with a flame. We're going to record what happens. Again, this is about energy. So I want you to think, what kind of energy do these have right now? Do they have any energy right now? Can you even make that kind of a call before you see the demonstration? That's what we have to figure out. Let's take a look. Now my son Logan is going to get a thermal picture of what's going on. As you can see, we got the thermal camera going. Not a lot in the way of heat just yet. You can hit record if you haven't already. Tell me when it's going. Okay, so on that camera, we're going to get a heat picture. Can you see the flame? Mm-hmm. All right, we're going to start on this side. I'm going to touch the flame to the top. I'm going to back away. Oh, that one's down. She won't work. What about the others? Oh, there we go. There we go. And the last one. Going up like a rocket. Take the lighter and light the tea bag on fire. And I want you to observe. Tea bag burns down. And then it goes up. Then it comes down again. Whoa.
Now that you've seen the demonstration, and I hope you stopped and took some observations down as well. You guys have been leaving observation areas in demo books blank. I'm not going to be giving you points at this point going forward if I don't see observations. That's what science is. It's not like copying down what I say. It's actually using your ability to make observations. After all, I got to prepare you for next year. Next year you are going to be expected to make your own observations and record them. So start doing that in your demo books, please. All right, your observations. Something got lit on fire. It eventually took off. Let's begin with the fact that even when the tea bags were just standing there, they actually did have some energy. Okay? And under the explanation, write down that this energy is called chemical potential energy. It's energy stored inside there. It's kind of like when you eat food, you actually are consuming something that has chemical potential energy. Your body's going to break that energy down, and you're going to use it to do things later. You're going to use that energy to, I don't know, play soccer in the backyard. You're going to use it, I don't know, to move your thumbs on a controller or whatever. Hopefully you're doing more than that. We'll see. All right? But when you eat things, you are actually storing chemical potential energy by breaking down other chemical potential energy in food. The tea bag, since it can burn, that fuel inside of it is actually a form of chemical potential energy. Once we light it on fire, we're taking that stored chemical potential energy, that ability to burn and produce heat, and it's becoming thermal energy, heat energy. And if you saw that thermal camera I had Logan using, you saw that when something started to burn, if there was this flare of brightness, that's infrared, that's heat light, that's heat energy that's being given off in the form of light, and we can see it on the thermal camera. So it gets very bright, it's giving off this heat energy, and well, what does heat make things do? Heat makes things expand. So as the heat energy warms the air above the tea bag, that air is going to actually expand. It's going to become less dense because the air particles are pushing all over. So there's an area of less dense air, or low pressure air, above the tea bag, and all the cold air around the tea bag and underneath it, that is more dense air. That is like high pressure. And what happens when you have a high and low? The high pushes towards the low. Less dense floats on more dense, and that cool high density air underneath the tea bag is going to push the tea bag up into the warm low density air. Again, less dense floats on more dense. And the tea bag rocket blasts off and flies up. And we saw it. Okay? The flying rocket is moving. Therefore, it has a lot of kinetic energy once it's moving up in the air, because it moves pretty quick once it starts to go. And since when it is moving, it's still on fire, and still, you know, if you take a look back at that thermal camera, you're still going to see a bright flare where it's going up. That means it's still producing heat, still burning, so there's thermal energy and chemical potential energy there. But I'd say there's more kinetic energy. Okay? Make sure you have this written down. Pause it. Write it down, but make sure you also have observations. You got to do more than just look for the place where I give this explanation. Okay, now your assignment on a separate sheet of paper, you're going to try and do an LOL chart for this rocket demonstration. right? And your chart's going to look like this. Again, it's an LOL chart. So we have an energy picture before. So this is right when the teabag catches fire. Then, again, the name of our system is the teabag rocket. So we have a before picture when it catches fire, and then we have an after when the teabag is blasting off and it's actually moving quickly up into the air. So what does the energy look like? Remember, we have a total amount of energy. All right. And I'll give you that. There's our total. Now the question is, what other kind of energy is there as soon as that teabag catches fire? Is there kinetic? Is there potential? Is there thermal? Look at the explanation. Think about it. Now where are these bars going to be? Then once it's blasted off, does it have kinetic, potential, thermal? The total amount of energy should still be the same. Okay, so the total is still going to be there, but how is the energy going to be broken down? It will be different than it is here. I would like you to complete that, take a picture of it, or complete it on a paint document. Doesn't matter. However you want to do it. Complete this LOL chart and upload it. It is due. Let's say it's due Monday. Okay, I want to see that on Monday. Perfect. Thank you.